young people particularly, a kinetic energy functional which works for at least molecules, particularly for molecules. I think it's a Nobel Prize winning problem. Just as Dr. Cole got, I still believe that if somebody can get a kinetic energy function of a molecule, functional, as a functional of rho, it's really a big problem solved. Because so many people in the world have worked on this. The earliest work of this was actually done by Thomas Fermi theory, for homogeneous electron gas. So that doesn't work, of course, for molecules. So what they showed is that this T of rho for the homogeneous electron gas is an integral, some constant, then integral rho to the power 5 by 3 r d cube of r. So it is very nice for homogeneous electron gas. And many have actually continued to use this for atomic and molecular systems, and obviously this doesn't work. But this is very simple, and this is basically the basis of the Thomas Fermi DFT. In fact, I must also mention that this Thomas Fermi kinetic energy term came much before the Weinberg and Kohn theory. Even before people knew the idea of unique functional, this was actually derived by Thomas and Fermi. There's a very nice paper on, in fact, in a very famous book by Density Functional Theory of Atoms and Molecules by Parr and Young. This is also derived in one of the chapters. The early DFT. So early DFT was actually done by Thomas and Fermi. So this was basically the Thomas Fermi theory. And people started talking about this in a very simple way. That then brought us to the final term of the universal function, electron-electron part. And now we know that the electron-electron part yesterday we discussed has two parts. One is Coulomb, another is exchange. If you do, and actually it requires rho 2. But I told you, at least for Hartree form, or a single determinant, rho 2 can be expressed in terms of rho 1. So half rho 1 R1 into half rho 1 R2 minus half of the orthogonal parts of rho 1, R1 R2, R2 R1. Multiplied by 1 by R1 2. One gave Coulomb, the other gave exchange. So the second problem is to write the electron-electron part of the rho as a function of the rho. So that is one of the main problems is to get the kinetic energy functional beyond Thomas Fermi. I must say that there are lots of exercise also to go beyond homogeneous electron gas, and there is a very famous paper by Weizsäcker, those who read early DFT, which is called Thomas Fermi Weizsäcker correction, but even that did not work. Okay, so TFW is called Thomas Fermi Weizsäcker theory, didn't work. So this remains a major problem. The second major problem is how do I write exchange? Remember, the Coulomb is easy. Yesterday I wrote it, rho 2, if I expand, Coulomb is the diagonal part of rho 1 into rho 1, so that's a functional of rho alone. So that's easy. So how do I write the exchange in terms of only rho? Just like in kinetic energy, I require orthogonal term. I showed that even for exchange Hartree form, I require orthogonal term. Single determinant. Let alone correlation. How does correlation change? I don't even know. So the third is the effect of correlation. Now, effects of correlation can be in exchange as well as the correlation part of VE. So this also I don't know. So these remain three burning problems of DFT, and none of them have been solved. None of them have been solved to the satisfaction. Obviously, people have done approximations, and people have worked with approximations, but nobody knows the exact solutions. So then I can write the VE of rho as J of rho plus K of rho, which is exchange, plus correlation EC of rho. So I break up again exactly by looking at the Hamiltonian and looking at what I know about Hartree fog. With that knowledge that the Hartree fog I can identify Coulomb and exchange, and then going beyond single determinant, as like in ab initio theory, is getting the correlation. So I must be able to write the correlation energy also as a function of rho. So if I can do that, then all my problems are over. So then I have just the phi of rho. So these are the major problems. So T of rho as well as exchange and the correlation remain the major problem. So what we can actually write is only the Coulomb part of the electron-electron repulsor and of course the external potential, exactly in terms of density. Nothing else I know how to write in terms of density. So this is something that I must admit first. Because even the Hartree fog exchange required of diagonal part, right? So I showed yesterday that formally VE rho is integral rho 2 R1 R2 1 by R1 2 dr1 dr. This is absolutely correct. So I showed it yesterday. This is exact. If I know exact two-particle density. But two-particle density is different from the density that we are talking of, rho of R. And the best I could do was for a single determinant, where I could write rho 2 of R1 R2 as half of rho 1 of R1 into rho 1 of R1 R2 of diagonal part, rho 1 of R2 R1 and rho 1 of R2. Of course, when I'm writing R1 and R2, these densities are basically the diagonal parts of density matrix. So I'm just writing it in a short form. They should be written R1 comma R1 or R2 comma R. But even this that I can write is only for single determinant. That means the effects of correlation I don't know. So this will anyway not give me correlation. But even then, exchange I don't know how to write. So I have severe problem in actually progress of DFT. I still don't know how to write exchange, even within the single determinant. And of course, I have no idea how to take correlation. Very simple matter. Just like Thomas and Fermi did for kinetic energy, the exchange was also done in homogeneous electron gas. At least the exchange part. Which again is not right for the molecular or atomic systems. So one actually wrote this K of rho, again in homogeneous electron gas model, as some constant C of x is equal to integral rho to the power 4 by 3 r dq of r. But it again was only for the electron gas, just like rho to the power 5 by 3, and you can start to do some exercise, at least for the exchange, if not for the correlation. This approximation was, of course, later they have a lot of change, was historically the first approximation, which is known as the local density approximation, which essentially means that the exchange which required non-local densities, even within the single determinant, can now be expressed in terms of only rho of r, and this became the beginning of what is known as LDA. So one of the first things that we can do is to forget about what we cannot do. What we can do is Thomas Fermi kinetic energy. We can write LDA. So let's try to do that and see what we get. So our energy then can be written in the following manner. I can now write the energy function. So one of the good things about DFT has always been that they have never been bottled by what they don't know. That's a good thing. Whatever they know, they made progress, little, and then eventually, of course, progress is taken place. So we can write then E naught of rho. So this is called the LDA, early LDA, with the Thomas Fermi kinetic energy. So some constant, let's say Ct, rho to the power 5, this is not important, what is the constant? d cube of r plus integral rho of r, sorry, v of r, d cube of r. So that's my external potential. And then you have a plus half of rho of r1 into rho of r2, 1 by r1 to d cube of r1, d cube of r2. So that's my Coulomb term, which is coming from expansion of this and put here. And this is, Coulomb term is historically a single particle classical picture. So there is no change in terms of Coulomb term. Whenever you do electron correlation, everything will change in extension correlation. So Coulomb term is a historical term, so there is no problem with this. It's basically coming from classical things. And then you have a Cx. So let me call this Cx, yes, I've already written it. Rho to the power 4 by 3 r. And forget about what I don't know. So I don't know correlation. So this is basically Thomas-Fermi LDA, where I put Thomas-Fermi kinetic energy, and then I wrote very beautifully the energy function now. And I can now start to do my calculations. How do I do that? For that, there is a second Van der Waals theorem. Yesterday I mentioned HK1. The second Van der Waals theorem is actually quite easy. So let me just write down the HK2, which became the basis of the beginning of practical DFT. So it says that, HK2 says that if I have an arbitrary density rho of r, and I calculate E0 as a functional of rho of r, whatever is my functional, then this quantity is always going to be greater or equal to the exact ground state energy. So this is exactly like a variation theorem. So instead of trial psi, I am putting trial density, because we have a psi star and psi. So it says that if I do this, then I get this greater than equal to E naught. So the HK2 prescribed the calculation of rho. So minimize E0 as whatever functional you take. It doesn't care, I don't care. Whatever you know, you do. Best you do. And that's the DFT objective, the best you can do. Of course, there are a lot of people who have done correlation. I'm not mentioning this, but I will just mention at least the functional. Minimize this, of course, subject to a condition that rho of r, dq of r equal to, don't forget this, that's very important. Because when I'm just varying the electron density, I have no way to know about the normalization. So I must make sure that the rho of r integrates.
So what are the variational parameters that you optimize in this?
Right now only rho of r. It's a functional calculus.
Right.
Okay? So when I come to Poincare, you will see that orbitals are green.
I see.
But right now it's just density. So it's actually a proper DFT. So the whole idea of writing this was, if you look at wave function picture, there are too many things. What are my variables in wave function picture? 4 electron waveform, 4n electron waveform, which even in single determinant consists of n spin orbitals. What is n spin orbitals? 4n functions. Because each spin orbital is one 4-dimensional function, so 4n. On the other hand, here I have only a 3-dimensional function. So however complex, why did DFT become so popular? However complex my system is, however large my system is, the energy is only a functional of a 3-dimensional quantity. So you have to understand what is the value of DFT. And so despite all problems, people didn't give up hopes. Because this is the, somehow if we can get a good approximation, this is the way to address large systems. And that is why DFT has become so popular, I must tell you. And it's only a 3-dimensional rho of r, which is still much easier than varying in Hartree-Fock. If you remember, we had to vary n spin orbitals. And then we got n one particle equation. Here I have only one function to vary, rho of r. But of course, I have to put a condition of rho of r, dq of r. Now obviously it will be very difficult for me to show for various approximations how the equations are obtained, but I am going to do for this which I have written, transform LDA. How do I get the equations? It's very easy to show. So of course, just like in the constraint variation, I first define my Lagrangian. So my objective function is E naught of rho, which I want to minimize, subject to a condition. So I must write a Lagrangian of rho, which is E naught of rho minus some constant, integral, I put some constant, integral rho of r, dq of r, minus n into some constant lambda. So that's my condition. So I hope for the students, again I want to repeat, when you put a Lagrange multiplier, this is for Lagrange multiplier, you write the constraint such that the constraint is equal to 0. So you put n on the left hand side and write the equation as something equal to 0, then that left hand side is multiplied by a Lagrange multiplier. Okay, so that is the reason we have done this. You can quite clearly see if I differentiate this Lagrange multiplier and this Lagrangian function L, capital L, with respect to lambda, partial derivative, when I do the variation method, I am going to get this equal to 0. Because lambda does not occur here, so it's a partial derivative, so this will be equal to 0, and I automatically satisfy this condition. So what I am now suggesting, with following HK2, I vary Lagrangian as a function of rho, with respect to rho, of course, tilde and lambda. The lambda, but this is a very popular correlation function. Then there is another one called LIP, Lee, Young and Parr, LIP function. So very famous B3 LIP functional, I must tell, is a Beckett-3 exchange. So exchange part comes from Beckett, which is of course beyond LDA, and the correlation comes from LIP. So then the correlation functional I am not going to discuss at all, but it is basically by some kind of numerical fitting. So people have actually found. So one could obtain reasonably good approximation. So one of the important functional is called B3B. The reason I am not discussing kinetic energy because this will be done in a different manner, cone sum. So I will come at that at the end. But now entire DFT has just these two parts. If I assume that I know how to solve kinetic energy by cone sum, I have only these two parts, exchange and correlation. So everything goes in that name. So it's a zoo of functionals. So I can't tell how many functionals are there. It's simply a zoo now because every day new functional is coming up. So there is no way I can write all functionals, but I can say what is B3 Lee, Beckett did exchange, Beckett 3 is a third person, so that's why Beckett 3, and Lee Young Parr is the correlation. So Parr, of course, P-A-R-R, Parr, he played a very important role in functional development. Robert Parr, he's the same person who did, for all people who remember, PPP. All of you remember PPP? Benzene and all that, Pariser-Parr-Popel model, right? So he's the same Parr who did a lot of work here, the LIP functional. And of course, many people also use BWN, correlation functional, with some exchange. Beckett, something. Most of the exchange is done by Beckett.
Sorry, it is started. Popel, I think, shared the Nobel with Walter Nobel.
Popel shared the Nobel with Walter.
So for this one?
No, Popel got for, see, the two words are different. Cone for DFT, that is clear. Popel for doing ab initio method, but making it popular through Gaussian. Gaussian was the work of Popel, John Popel's group. So he got mainly for Gaussian, but of course he